Okay, last week we ended off talking about particles, looking at matter, describing some of the properties. What we're going to do this week is we're going to continue off of that idea of describing matter, and we're going to continue from the video that you just watched on the different states of matter. The different states of matter, you're talking about particle motion, describing matter. So, in essence, you're talking about the kinetic molecular theory. You're talking about particles right here, particles that are going to be constantly moving around. Now, even when they say that something has reached absolute zero, which cannot happen, there's always going to be some residual energy somewhere. But imagine that you have these particles, and these particles are vibrating around, and as they lose kinetic energy, they lose that motion, they start to slow down some, and that is going to represent a temperature change. So as the particles start to lose energy, okay, so this would be like energy that's leaving the system or those particles. So you have energy that's leaving, and energy loss. When that occurs, the temperature decreases. All right, so the temperature goes down. Now, theoretically, if we could reduce the energy enough, we would stop particle motion. These two little atoms would no longer move around, but there's always going to be some residual motion. But the idea that I'm talking about here, we're talking about particles in motion, something in motion, kinetic molecular theory. So kinetic energy deals with the speed of particles. Actually, you're looking at the average speed when we're talking about the temperature change. So you're looking at all of the particles, not just like one particular one. Okay, so you're looking at an average of them to figure out what your temperature of that object would be. Now, the temperatures at which these objects are will help determine what state of matter they would actually be in. So there's actually 5 types that we will mention in the video. They went over more kinds, but there's 5 types that we'll mention in here, and really only focus on 4, well, really only focus on 3 of them, but we'll look at the 4th one. So just as a quick recall, when we're talking about kinetic energy, kinetic means that something is in motion. And from the first half of the year, when you guys really loved the physics stuff, you had a formula that was 1/2 mv squared. Well, if we're talking about energy, well, particle motion, a car moving down the street, you're talking about something moving. We used the unit joules in the first half of the year to describe work and energy. Well, in the second half of the year, when we're talking about particle motion, temperatures rising and lowering, you might come across different references on the internet, in the textbook. They might use joules, but what we will be using is the term calorie. Now, you guys should be familiar with the term calorie, because whenever you go to eat any food, you know that you're consuming calories. You're actually consuming what's called a dietary calorie. A dietary calorie, 1 dietary calorie equals 1 kilocalorie, or 1,000 lowercase c calories. Right? And we'll dive more into what this actually means in terms of calories later on. But the conversion to go from what we were talking about in the first half of the year to this second half of the year is simply that 1 calorie, energy needed to raise 1 gram of water 1 Celsius degree, that would be 4.19 joules worth of energy. Okay, so if you're looking at just conversions, you're looking at 1 foot equals 12 inches. Well, inches, you have 1 calorie equals 4.19 joules. So, temperature changes, the average, see, just like I said before, the average kinetic energy. That's what your thermometer is actually going to be measuring. Now, the 3 temperature scales that you are familiar with, you've got Fahrenheit, that's what we all use in the U.S. You have the Celsius scale. That's what we're going to use for all of our measurements in the class. And then you have the Kelvin scale, which is really simple to use because you just take whatever your Celsius temperature is and you just add 273 to it. So if we go back to looking at that absolute zero where all of these particles right here, as these particles are moving around, when they cease to move, when they stop moving, that means that they would have an average kinetic energy of 0. So we'd have 0 Kelvin. Okay. So you'd have 0 Kelvin, and what would we be looking at for other temperatures? Well, if you want to figure out what that would be for Celsius degrees, you'd subtract that 273 from it. We're not going to worry about converting from Celsius to Fahrenheit. We have reference points. Everyone has to remember these, okay? And at this point in time, you guys are old enough that you guys should know what these temperatures are, at least in Fahrenheit. You have the temperature at which water begins to melt, okay? So you have an ice. Okay, you have a solid that's going to melt into a liquid, and the temperature at which it is going to melt into a liquid is going to be that 32 degrees Fahrenheit or 0 degrees Celsius. Now, something that I'm not sure why people have a difficulty understanding this. If ice begins to melt at 32 degrees Fahrenheit, at what temperature do we have it going from a liquid to an ice? Now, liquid to an ice is at 32 degrees Fahrenheit, 0 degrees Celsius, and that's what we would say is our freezing point. All right. Now, on the opposite side, if you have your liquid and it's going to change to a gas, that's going to happen at 100 degrees Celsius or 212 degrees Fahrenheit. All right, so with that, we have vaporization that's occurring. So I'm just going to abbreviate it there. We have vaporization that's going to be occurring. That's where your water is going to start to boil. It's going to start to vaporize, change into a gas. So on the flip side of that, at what temperature will gaseous water begin to liquefy? Well, that's going to be at 100 degrees Celsius or 212 degrees Fahrenheit, and we're going to say that that condenses. Now, can we jump from one thing to another? Can we go directly from an ice over to a gas? Sure you can. That's called sublimation. All right, can you go directly from a gas right to an ice? Sure, that's called deposition. So we'll talk more about that later on. All right, we already mentioned the 0 Kelvin is absolute zero. I gave you that one conversion where you're talking about the negative 273 degrees Celsius. It's almost as if I've gone over that twice for a reason. I wonder what that would be. All right. So let's look at these 4 very common states of matter here on the Earth. We have the first one. You have solids. Now, I know what you're thinking. I know what a solid is, but I'm telling you right now, if you don't write this down, typically what happens is people take and believe they know everything and they're going to remember everything with solids, liquids, gases, and they get to the test and then they forget something. So do yourself a favor and just write down a couple things on your paper so that way you have it. All right, so if we're looking at solids, in terms of solids, energy, the energy associated with solids is going to have the least amount of energy of our four types, right? So it's going to be our lowest amount of kinetic energy. And if we're describing the particle movement, we would say that they're vibrating about a fixed position, okay? So these particles right here, they're just going to be going back and forth, but they're not really moving around inside of the container from one side to the next, to the top to the bottom. Because they are only vibrating about a fixed position, we say that they have a fixed shape. That fixed shape, if it has a fixed shape, then it only is occupying a certain amount of volume, a certain space. So these particles, you can kind of describe them as having a lattice or this perfect crystalline structure like this right here, okay? Now, in terms of compressibility, are you going to be able to compress these solids very much, if at all? No. So solids, they're not compressible. We go to liquids. Liquids, they are going to have a little more kinetic energy than what your solids have, okay? Now, they're going to have enough kinetic energy that the particles are going to move freely with respects to a specific volume. All right, so when I say that they move around, they will move around only with respects to the volume that it is. It is not going to fill the container. It doesn't do that. These particles will slide and move past one another as it sloshes around inside of the glass there. Okay. In terms of shape, because they are able to move more freely, because they do have a little more energy, they're able to have a flexible shape. So if we poured these out onto the table, those molecules of water would spread out evenly across the table. If you put it back into a glass, it would take the shape of the glass up to what the volume of liquid would be. And liquids, they are not going to be compressible. All right, that is an extremely important concept to know if you ever plan on driving, because your brakes in your car operate on this principle that the liquid that's inside of your brake lines is not going to be compressed. So right here, I have inside of your hood of your car, you have the brake fluid reservoir tank. All right, and this is a crude drawing of your brake lines that lead down to your caliper, and those calipers will bite onto the rotors of your car, causing friction, slowing your car down. So what happens here is, as you apply pressure to the fluid, you press on the brake, that fluid applies pressure equally in all directions. In all directions. So when that fluid is being compressed in all directions throughout the entire brake line, you have these little brake pads, and the piston causes those brake pads to squeeze onto the rotor, causing a greater amount of friction, and that slows you down. If you're ever driving and you feel like you're putting your brake pedal all the way down to the floor, or it feels that, a lot of people, they describe it as, they say that it feels kind of spongy, okay? If that ever happens, more than likely what has occurred is you have little air bubbles that are inside of your brake line. Air is compressible, liquids aren't. So when you apply pressure, and that pressure is exerted throughout the whole line, when it gets to the little air bubble, it's going to squeeze the air bubble instead of closing those brake pads onto your rotor. And that's not a good thing. All right, so you'd have to have the brake line's blood, is what they say. All right, so we have our fourth state of matter. Our fourth state of matter is going to have a greater amount of kinetic energy. enough kinetic energy that the particles are now freely moving about the whole entire container. Now, if they're moving about in the whole entire container, they're going to have a flexible volume, and because they're moving around, they're going to have a flexible shape. So gases, like I mentioned before, gases are compressible. All right, so are compressible. Now, if they are compressible, where do you guys use this idea of compressibility of these gases? Well, you have an air compressor. If you have an air compressor, as the air compressor is running, it's putting more and more and more air into the tank, filling it up, and it produces a high pressure inside of here. Then you use a hose and then fill up your tire of your car. As you add more air into this, you compress more and more air, increasing the pressure inside of it. All right, so a little side note, what's going to have a greater amount of pressure? You're going to have a greater amount of pressure with a bicycle tire or a car tire. All right, well, you're going to have it with the bike, higher pressure with the bike tire, because when you're looking at the surface area for a bike tire, it is very, very small. All right, so if it's supporting the weight, you're talking about a lot of pressure being applied to a single point on that bicycle tire. You have to have a higher pressure. But if you get a great big car tire, by comparison, you have a greater surface area, so they do not have to have as much pressure in there to support it, because you got a larger surface area there. All right, we have our last state of matter that we'll take a look at. We have a plasma. In a plasma, you're talking about a very high amount of kinetic energy. All right, what plasmas are is they're ionized gases is what they are. Ionized gases, you're talking about the sun. You're looking at cathode ray tubes, fluorescent tubes, fluorescent light bulbs. You're talking about charged particles that are moving through a gas. You're looking at lightning. So here's the deal. A lot of people say, oh, solids or liquids, they're the gases, they're the most common state of matter. No, if you're looking at the sun by comparison to the earth is just this tiny little blip compared to the sun. So if we look at the sun and the sun is a type of plasma, then that is significantly larger and would have more matter there than it would on the earth and all the solids that you could imagine. All right, those four states of matter, we can have them change from one state to the next by simply increasing the amount of energy. You increase the amount of energy, you go from the solids to liquids, melting. You have the liquids to gases, vaporizing, and then you energize those gas particles and you get a plasma. If we go from a gas to a liquid, you have vapor condensation. And then if you go from a liquid to a solid, you have freezing. Right here, this is based on our time here. We got to be coming up close to the end of the period. So the last thing I will mention is that this chart right here, we're going to use this quite a bit over the next 2 days. So we need to mention a couple of terms here before we wrap this up. And I want you to write this down on your paper here. If you have this portion, let me choose the yellow here. You have this portion right here. That is the part where you're looking at ice. Okay? So that is going to be ice. If we give you anything, any numbers that are going to be between 0 and negative 273, that is going to be ice. And we're going to use this formula. I don't really write it out that way. That's just this graphic. I say CMAT. Okay. When I get in tomorrow, the C is going to stand for the specific heat. M is going to stand for the mass. Delta T is a change in temperature. We'll talk about the formula when we get in there. We have the liquids. Liquids are going to be anywhere between 0 degrees and 100 degrees. I don't care what temperature it is. If it's 53, 82, it's going to be in the liquid state. We're going to use, again, that formula, Cm delta T, but what's going to happen is we're going to have a different specific heat, a different rate at which liquids heat up and cool off. When you get to 100 degrees, here we have a gas. And again, gases, you're going to notice you have that Cm delta T. All right, well, gases heat up and cool off differently, so they will have a different specific heat. So you can see this formula is not going to be something difficult, because I'm going to give you what these specific heats are. So if you can remember CMAT, then you'll be okay with the formulas and doing the simple math with this. All right. For right now, I don't want you to submit these notes. Just hang on to them. We'll finish them up tomorrow.